Class example 1.34 asks us to apply a stretch to both the graph of a function and to its equation. Here we're given f of x equal to negative x minus 2 squared plus 9. So this is a quadratic function, or a parabola, given in vertex form. We know from that negative coefficient that this will be opening downward, and that its vertex will be at positive 2 and 9, as shown in the graph. So then it says the graph of g of x is obtained by vertically stretching the graph of f of x about the line y equals 0. Well, as a reminder, formally we would often simply say that it will be stretched about the line y equals 0 and will not include the word vertically. But we know it's vertical because the line y equals 0 is the x-axis. And when we stretch about the x-axis, that is always a vertical stretch. Next it says this will be by a factor of 3, so all the y coordinates will be multiplied by 3. And then there will be a reflection in the line y equals 0, again the x-axis. So when we see that vertical stretch, we know that when it says a factor of 3, that's telling us the a value, and because there's a reflection, it will be a negative a value, so negative 3. One thing that can be really helpful when you're graphing multiple transformations is to represent the transformations using a mapping rule. So here, because both of our transformations are vertical, they'll both reflect the y coordinate, so xy becomes x and negative 3y. This means if we wanted to transform our graph, we can simply take each point and multiply its y coordinate by negative 3. Let's try this. So for the vertex of 2 and 9, we will multiply the y coordinate of 9 by negative 3 to get negative 27. We're asked to repeat this same process and to indicate the new location of the x and y intercepts and other key points. Given that we're graphing a parabola, the vertex and the intercepts are basically all of the key points. If we had a more complicated polynomial function or a piecewise function, we might have some other local minima or maxima to indicate, but here the intercepts and the vertex would probably be sufficient. We'll note again that the x-intercepts, because they have heights of 0, will remain invariant under this transformation. So looking at a result, we now see a graph of a parabola opening upward with a vertex at 2 and negative 27. If we write the equation for g of x in terms of f of x, it would be g of x equals negative 3 f of x. This is because there is a reflection and a stretch by a factor of 3. When we want to write this in terms of x, we would now replace f of x with its equivalent expression of negative x minus 2 squared plus 9. And as we distribute that negative 3 through, we see that it becomes positive 3 x minus 2 squared minus 27. And that makes sense given our corresponding graph, because our graph was opening upward, so a positive a value, and had its vertex at positive 2 and negative 27, which we now see explicitly in that vertex form. Again, the location of our invariant points will be on the x-axis. If we wanted to determine their exact coordinates, we could take that transformed equation in green, y equals at 3 times x minus 2 squared minus 27, and replace the y value with 0. We would then solve for x. This graph, we can clearly see the integer values of 5 and negative 1, so that's not really as necessary, but could be helpful in another case. A parabola will always have either a maximum value or a minimum value, and will then extend to either positive or negative infinity. So in our original graph, we went from negative infinity up to positive 9. As we can see in the graph of our green graph, we now have a minimum height of negative 27 going up to a maximum of infinity, which we never reach, hence the rounded brackets. Let's continue class example 1.34 with the same quadratic function, but this time, rather than having a vertical stretch and a reflection, we'll simply have a horizontal stretch. Now the question is going to say, given f of x equal to negative x minus 2 squared plus 9, that h of x is obtained by horizontally stretching the graph about the line x equals 0. I remind you that we don't need to say horizontal there, because once we've said about the line x equals 0, it is implied that it's a horizontal stretch. What's important here is we're going to start by writing the mapping rule. And we're going to do that because we're working with the graph. We want to sketch the transformed graph. When we read in words that the horizontal stretch factor is 3, a lot of students question, should I be writing the reciprocal in the mapping rule? And the answer is no. When we write a mapping rule, we are representing the effect on each point. And a horizontal stretch by a factor of 3 has as its effect to take each point 3 times as far away from the y-axis. So it really is multiplying the x-coordinate by 3. The only time we see the reciprocal relationship is between the stretch factor and or the mapping rule and the equation. So later in the next step, when we write the equation, that's when we'll see the reciprocal. We'll label each point here, and now let's go ahead and multiply the x-coordinates by 3 to see the transformed graph. I am a huge fan of using the mapping rule to graph transformed graphs because it helps us avoid common errors. And I'll call them oopsies because you probably didn't even mean to do this, but often when students are asked to stretch something horizontally and they're working on the graph, rather than doing it about the axis, they do it about the vertex, which is to say they keep the 2, 9 at the point 2, 9, and then they move the points below that further out. All points are on kind of a canvas here, and the canvas is being stretched, right? So every single point, even the vertex, is moving 3 times as far away from that y-axis. So the point 2 and 9 becomes 6 and 9. Notice our y-intercept being on the y-axis did not move because 0 times 3 is still 0. That is our invariant point of this graph. So to write the equation for h of x in terms of f of x, we need now to write the b value. Well, the b value is the reciprocal of the horizontal stretch factor. Otherwise said, the horizontal stretch factor is the reciprocal of the b value. So since we've stretched by a factor of 3, the b value must be 1/3. To write our equation in terms of x then, we would take the original equation, and in every instance of x, so in this case in the bracket where it's at x minus 2, we would replace that x with 1/3 x. We can check this in our graphing calculator and confirm that it gives us the properly transformed graph. Simplifying this, or rather factoring it to represent it differently, is a little bit tricky, because we have to factor the 1/3 out of the binomial of 1/3 x minus 2, and when we divide that -2 by 1/3, it becomes -6. Notice that the square, which is to say that the exponent of 2, is on a bracket outside of both the x minus 6 and the 1/3, but not the negative coefficient. So now we can square the 1/3 without squaring the negative sign to achieve a final state of y equals -1/9 x minus 6 squared plus 9. As mentioned earlier, our invariant point was at 0 and 5.